Hello and welcome to this low-level JavaScript video where today we're going to be building a bit unpacker. Well, it's actually the second episode in kind of like a micro series, I guess, building a bit packer. And yeah, we're kind of just doing the other half of the equation here, which is like taking a packed buffer and kind of unpacking values for it. So if you haven't seen that first episode, I mean, I do advise that you go and watch it because I think it will just make the most sense. But you could probably get away with not watching it, or just at least watching this one first and then going to watch the other part of it. I think these are going to be kind of it's all part of one big API, but they're kind of two very distinct steps. The packing and the unpacking. And the unpacking is not quite the same as the packing. It's definitely going to be quite a different API design at the very least. So I think it stands on its own. You can be the judge of that. If you haven't seen that first one, let me know how it goes. Alright, so just as like the briefest of recaps as to what a bit packer actually is, well, it's basically a tool and kind of an algorithm to take a set of data, like a bunch of bytes or something, and that data, the idea is that you are not using all of it. Like, you're not using all the space that's available to you. So you might have a bunch of bytes and you only use 6 bits here and you only use 3 bits for this, and then maybe there's like 5 bytes in a row that only use 1 bit. And the idea is that you take all of those small representations, you take all those like a description of like, here's where some of my data is and here's how many bits it is, and you squish that down into a smaller buffer. As you just take out all the unused bits and you just pack everything together. And obviously that is like a super rudimentary form of compression. It's actually kind of just the mechanical aspect of the compression. It doesn't dictate any of the smart stuff that actually goes into compression. It just does the job of like taking a smaller amount of data and squishing it together into just a smaller buffer size. And yeah, it's going to form the basis of some upcoming compression stuff that we're going to do. So that's the packer. And the unpacker, well, it's kind of like a parser for your packer. You can take your packed data and some kind of description of how to unpack it. And that description could take many different kinds of forms. We could pass it like a dictionary of values that it could look for to grab stuff out. We could pass a function in which we give the user a pattern of bits and they tell us whether or not it's a match that they care about, and then we kind of offload it to them. Yeah, there's kind of a bunch of different ways that we could do it. Obviously on this channel I've discussed parser combinators in the past, and you can use parser combinators as well on binary data. I have a library arcsecond. I've used it in some of these videos as well. There is a whole set of binary parsers in arcsecond, and actually at some moment I went in and I kind of overhauled the whole design so that arcsecond is always working on binary data actually. Even when you're parsing text, it's still like you could parse text and binary data at the same time. Which is actually quite useful when you're parsing binary data, because sometimes there is actually just text in there. And this allows you to use all the nice familiar tools for that. Anyway, that's beside the point. That's not the kind of parser we would be building here. This is going to be a much simpler thing. It's just going to be recognizing patterns of bits. But the important thing to get right here, and the important thing that I kind of want to cover, is I kind of want to do this with like a kind of lesser used pattern of iterators. I mean, they're lesser used in JavaScript and TypeScript, but like in some languages, iterators are really like, a really big fundamental block of the language and everything is built around them. So yeah, they're a useful tool. I think they're going to be a good fit for what we're doing here. So without further ado, let's just jump in. Let's zip over to the code. And I still have the code from last time. And at the end, I kind of hinted at a possible looking API design using iterators, and the idea is we would create an iterator using like this bitpacker create unpack iterator static method. We'd pass that a packed buffer, and then we would pass it a function for recognizing patterns of bits. And the user can put whatever they want into that function, right? All they have to do is return either a new value or null or something like that to basically indicate to the iterator, like, do we recognize this bit pattern? Are we going to transform it, or are we going to reject it and say we don't see this yet? Maybe give me a new pattern and I'll see if I recognize that. The one thing I think I discussed last time that I actually think I'm going to change is I suggested that we could kind of do a two-part thing where basically we would recognize patterns and we would allow the user's function to also transform them into a new form. So maybe we turn them into a number or turn them into whatever. And I think I'm not going to do that. And I think the reason I'm not going to do that is because if, for instance, the user just wanted to get like the result of a bit pattern out, just wanted to get the same bit pattern as a string out, and there's a reason that we have to do this as a string, right? Because, well, we could do it as various different kinds of implementation, but I think a string is the least intrusive. The reason we have to do it as a string is because sometimes we might need to recognize a pattern like 0, 0, 0, 0, 1. And if we were to use numerical values, we would only be able to recognize the value 1. We wouldn't be able to see that, for instance, that there were 4 leading zeros there. So that can be problematic. We could get around that by having like two arguments to this function, one which states the number of leading zeros, and the second which is just the value. But yeah, I think just sticking with a string API is probably going to be like fine for this, especially for what I want to do with it in the coming videos. And we'll see, maybe there are can make different options for how this works, but I think this is going to be my idea now. And the idea then, since we're just dealing with strings, and sorry, I think I didn't finish my point about the fact that I was talking about transforming the values. So if we were to have this, like match this pattern, what we could do, for instance, from our function is do something like this, right? Pass in the pattern and some, like, then pass the pattern, right? We actually wouldn't even need to do that because we kind of see our pattern here, so we could just return the number like that. But yeah, maybe we've got a more, like, maybe you even have like a regex inside here which is matching a certain bit pattern. I mean, that's perfectly possible in this API, and in that case you might want to do like a pass-in thing. The reason I don't want to do this is because if the user is just going to pull values from the iterator and they want the bit pattern, well, in that case, no, I guess this would also be fine in that way. Yeah. Okay, so I think what we'll do, yeah, maybe that is the most flexible API. You can see I haven't done a whole lot of preparation coming into this. I think that is going to be the API I go with. All right, so enough kind of prognosticating over this. Let's actually go and write this this function. So this is our pack into buffer and our pack function, both static methods. Sorry. Let's make a static unpack, or create, what was it? Create unpack iterator. And this is going to be a function that's going to return an iterator. And the user can use the iterator to just keep getting values. And I think what I'll do inside here is like probably write a generator function, and we'll return the user a generator function. Perhaps this could even be a generator function. Can that be the case? Can I do this? I think that's legal, right? Yeah, that looks good. Okay, so let's do this instead. Excuse me. So we're going to want to take some generic argument here, so that the user can tell us, and the type system in TypeScript, we're using TypeScript here. I mean, if we were using JavaScript, this wouldn't matter, but just the fact that we're using TypeScript, we can be a little bit more explicit about like kind of the library's intentions and the user's intentions. So I'm trying to remember now where the generic part goes on a generator function. I think it's here. We're going to take a t, and that's anything, that's any type. The user is going to tell us that type. And we're going to say that we need a packed buffer. So I'm going to call this thing packed. I'm just going to call it buffer actually, because why would we call it packed? That'll be a UNA array. And the other thing we're going to receive is a function which is going to take in a string pattern of bits and return a t, right? The t is what the user tells us they're going to return. So let's do that. Something that takes a pattern with a string, and this function will return a t. Oh no, I'm kind of now like inlining a function here. Let's put the type of this function outside. So let's do type unpack function. And that's going to be an unpack function of t because we need that t there. We take a pattern, which is a string, and we return a t. Okay, so then we're going to take our unpack function, which is of type unpack function t, right? We get the type in and we're kind of passing it down the type chain, as it were. Yeah, and that's it, right? So we're inside this generator now. So when the user calls this function, they're going to get an iterator out. And they can call next on that iterator and get values. So for us to do that, we're going to need an index, like a reading index. I think this is going to mirror the pack into buffer somewhat. Yeah, so we're going to need an index. So can't have const because we're going to be mutating it. We're going to have an index, and we're also going to have a bit index. Just like in the pack into buffer, right? Because we're going to get this buffer, and the bits are packed from left to right in each index, and we can read out eight bits at a time, and then we need to go to the next index, and then we'll set our bit index up. So what we will do here then is while the index is less than the buffer.byte length, we can do this whole thing. What we might want to do, no, we'll get to that in a second. Okay, and then I'm going to have another mutable variable called pattern. Yeah. Okay, so at any given moment, what we're basically going to do is pull a bit from the buffer, put it into our pattern, like add to the pattern, and then we're going to give that to the unpack function. The unpack function is going to tell us whether or not that pattern is a match. So we might first pull one bit and it's not a match because, you know, why would you match one bit? It doesn't really make sense. Maybe it takes us a few bits to add on, but maybe after 5 bits we get a match. And then what we actually do is we take those 5 bits and we yield them back to the consumer of this API. So basically when the user is calling next, what they get back is those 5 bits. And then we just continue on from there. So let's take a look at that. By the way, if this is your first time seeing a generator function, it's probably quite confusing now. A generator function is not like a regular function. It's a function that is kind of like an async function in a way. You can, in an async function, you have like, you know, asynchronous stuff happening. And you can use this word await. And when you await something that's a promise or another async function, basically kind of the code kind of pauses there until that's done, and JavaScript can do other stuff in the meantime, right? It can do other asynchronous things, so it can run multiple asynchronous things at the same time. And when you do an await, what you're telling JavaScript is, hey, just wait for me to be done because I'm not doing anything until I've got this thing back. And yeah, so generator functions are a little bit like that. They also have a yield keyword, and they're also kind of asynchronous in a way, but not asynchronous in the way of like async functions. They're asynchronous in the way that the user can call into the function, this generator function, or this generator functions when the user calls next on the iterator. And what happens is it runs all the code it can up until it hits a yield statement. The yielded value comes out of the generator, and then the user can do something with that. And then when they call next again, the function begins from where it left off. So it's kind of like an interruptible function that we can start and stop. And that's why it makes a good fit for this, because the user is in control of how often they're checking all the patterns. If they get to a point where they no longer need information from this packed buffer, they just don't call next anymore. It's that easy for them. Yeah, so that's kind of why it makes a good match for this API. All right, so while we have an index less than the buffer byte length, we're going to take our pattern, we're going to grab a bit from it. So we're always going to be pulling from, excuse me, we're always going to be pulling from the buffer at index, at this index, but we only need one bit. And the bit that we need is like indexed by this bit index variable, right? That's how it works. And if you've seen the previous, part, you'll know that the way in which we can like isolate a bit is that we take a 1 and we shift it up to the bit position. For instance, in this case 7. It should have been bin. And what that does is that gives us a binary number where where the position of that 1 corresponds to the position of that bit, right? So that is bit 7. If we did this for bit 6, we would have it in the 6th position, and if we did this for bit, bit 3, it would be in the 3rd position from a 0 index perspective, right? Because index 0, that's down here. Okay, so what we want to do is we want to use this technique to create a mask, and that will be 1 shifted up by the bit index, and then now we will have isolated that bit inside the number, right? So let's say our number was something like I don't know, like 11011010. Yeah. Let's say our number was something like this. That's right? That's 1, 2, 3, 4, 5, 6, 7, 8. Yeah. And then if we AND that now with put that inside the binner function so we can visualize the binary. If I do 1 shifted up by 7, what we'll see is that like we match that 1 there in that position. We got that 1. If I do 6, we're going to get the 1 that's in that position. If I do 5, there's actually a 0 in that position, so we don't get anything. Now, the problem is that if we do this with 7, for instance, we want that 1 bit, but we kind of want it like on its own. We want it down here. It's on the wrong side. It's too far that way. It's in the 7th position still, right? Because all we've done is isolate it, but we need to shift it down to get it into the right position. So we can just wrap all of that in a shift right by 7. Not 7, by bit index. If we did 7 every time, it wouldn't work correctly. I've used the logical shift here, which means we only ever shift, when we shift, do a right shift, and we shift a bit down, the bit that we kind of pull in on the left-hand side is going to be a 0. That's kind of what that means. Alright, so that's our pattern. Then we need to check our pattern. So like we can check if it's a match by running our unpack function on the pattern. And if it is a match, that's great. We're going to yield the pattern back to the user. And then what we can also do after that is set the pattern to an empty string again, because we're done with those bits. We can also, after we do this, before we do anything, what we can actually do is like subtract 1 from the bit index, because we're done with this bit index now, right? We've read a bit from it. We should immediately decrement it. So here we've matched the pattern our pattern's now empty string again. Of course, the user has received this and the code stops at this point. The user can do something with that pattern, and then when they call this the next time, we'll set the pattern back and we'll be jumping back up. But before we jump back up, we need to check, like, is the bit index now equal to -1? If it's equal to -1, that means we did every bit in that byte, and we need to go to the next byte. So we can actually say that the index increments and bit index goes back to 7, because we're going to the beginning of the next byte. And with that, that is probably it. And I'm just realizing now that we did this whole thing with the T and everything, and I'm not doing that correctly. So what we should do is say const like transformed pattern value, and that's going to be this. That's going to be when the user runs the unpack on it. Because in that moment, maybe they turn it back into a number, maybe they turn it into a character or something like that. And what we need to check in this moment is if this is not equal to null. So what null is going to signify in this situation is that the user didn't get a match and they haven't transformed anything. And that the unpack should just continue with the next bit. That of course creates a limitation in that it means you can never return a null as a value. That is kind of a trade-off I'm willing to make here. I think it's pretty rare that you would need to return null as like a signifying value. Especially if you're the kind of person who's going to get angry about that kind of API, like returning null as a signifying value. I think you're the kind of person who would also never want to return null, because you wouldn't use a value like null inside your program anyway. So it's probably not a problem. It might be something that people trip over, but I think it's okay. Probably no one else aside from me is ever going to use this API, so it doesn't even matter in that case. But yeah, so I think that might be our unpack iterator. So let's try and see if that works for us. Now let's think about how we could do this then. So let's get values. Let's call this unpacked. And how we're going to do this is we're going to say, we need an iterator, of course, right? So our iterator is going to be bitpacker.create unpack iterator. We'll pass our packed buffer into it. And our function, notice right now it says unknown because it doesn't know, like we haven't specified the generic type to this function. TypeScript could still try to figure that out through inference. So if it understands like what we end up returning from this function, it will actually be able to figure out the type of this. So maybe let's just try and see if it's smart enough to do that. So pattern it should know is a string. Excuse me. And let's do this thing that I said is completely pointless before. It's a good illustrator because it means we don't have to do anything special here. But what we could say is if the pattern is equal to 0, then we're going to return, let's just return the pattern. Actually, in this whole case, let's just return the pattern. Like, it's a really simple one, but in both those cases, it's going to return a 0 or a 1. The world's simplest unpacker, just give me all the bits. And then what we can do, right, is we can just say binary string is going to be iterator dot. Could actually like allow the iterator to fully kind of empty its contents into this array, and then we can take a look at the binary string. So let's see if that works. So we got a big binary string out. It's not actually a binary string. It's a it's an array. But if we do binary string dot join here, just join it, all the characters next to each other, what we can actually do is take all of these, well, alright, now what you'll see is that if I highlight these, they're actually going to match. But there is something weird going on, right? We got a bunch of extra zeros on the end. Now, if you've seen the previous episode, which I hope you have, this is going to make perfect sense because we have a buffer here, right? We passed a packed buffer. It's byte aligned. It has to be byte aligned. So if we didn't have enough bits when we went to pack, like we didn't pack a full like byte aligned buffer here, it's going to end the buffer with zeros. And so this is not that useful for us because that data is not really part of a representation. So if we were to write this very simple unpacker, that's actually not going to like help us at all. So the better way, well, we could actually do something even like this, right? Let's do this. Let's make a switch inside, and the switch is going to be the pattern. And in the case that we see 101, wait, let's do it like this actually. If we see the string 01, we're going to return 1. Simple. And then that's going to kind of catch that next case as well. If we see the string 0001, I think that is, then let's return, what should we return from this one? It's kind of also 1, but let's return like something that's very clear to us. Let's return -1. So that kind of like now we're isolating different parts of this, right? It's not a direct one-to-one unpacking. I'm just trying to illustrate here that how we can pass out individual values. Then we might see this string, for instance. So that would be case 1000, return 1000. Then here we get a whole bunch of ones in a row. So let's match 1 1 and return 3 from that. And then that should take care of all of that stuff. Is that right? No, because we don't have 1 0. The nice thing about this, right, is that you can also, using this kind of parser, you can write a priority decoding. So we could first try to decode 1000, and then after it, like, we could also try to decode. No, that doesn't really make sense, because you would never get to that point. So please disregard that. That doesn't even make sense. I'm just trying to think now how we could actually do this. So was that, how many ones is that in a row? It's 10. Oh, that's actually fine because we'll capture all of those. We have a 0 on its own, but that will capture a 0 1, and then we'll get 1 1. So this should actually pass all the data, and then if we get anything else, we'll return null. Because that doesn't match into our decoding. And I'm just trying to think, is this going to allow us to avoid capturing all those zeros at the end? I think it actually is, because we will never match them. We will never actually get to the point where they match, because we'll always return null, and therefore the iterator will end and we'll fill it up. So let's just see if that actually works. Now we get a binary string and it's empty. So that's unexpected. That's not what I expected to see there. Let's try and work out how that happened. Well, one reason that might have happened is because that is not correct. We're yielding the pattern out here. but I would have thought that we would still have seen something. So it's still empty array. Let's see what's going on here, because that doesn't appear to be working correctly. Alright, so we've got our index, pattern. So we bring in the first bit, it's a 1. We try to get a transform pattern value, we get null, that's great. Come down here, bit index equal to -1, it's not, so we jump back to the top. So bit index should now be 6, we should be grabbing the next bit along, which hopefully is a 0. So we get pattern, that gives us 1, 0. Excellent. Now here, let's jump into our unpack function, because this should be giving us a thing here, right? So we get pattern 1, 0. Oh, yeah. I thought we'd written a 1, 0 implementation, but I guess not. Is that going to mess anything else up if we do 1, 0 here? I don't think so. So let's just do this. Refresh and optimistically let that run. And there we go. Nice. Okay, so what does this look like? We get first a 1, 0, so we end up with 2. And then we actually capture another 1, 0. That's what I didn't realize in the first place. So then we get another 2. Let's actually just print this down here. Binary string. And then we get a -1, and that is because we see 0, 0, 0, 1. So we get -1. That seems correct. Then we get 0, 0, 0, 1 again. Interesting. So we get another -1. Then we get, how many 3s is that? 1, 2, 3, 4. 3s in a row. So that's 1, 2, 3, 4. So then we're up to here. And then we get 1, 0 again. So we see, is it 1, 0? 2. Yeah, so we get a 1, 0, which is a 2. We see another 1, 1. And that is a 2, and then that's the end, right? Because then there's nothing else to match from here. We can't, well, that's not true. We should match one more 1, 0. Yeah, and then we see a 2 in the end, right? So that is kind of the end of the whole thing, right? We get this 3, 2, 3, 2. And then there are no more bits for us to match after that. Yeah, excellent. So we ended up matching one extra bit there, which is not part of our encoding, but this is also not what our encoding is. So that doesn't make sense. And we could, just for the completeness, we could not exactly sure what happened there. We could put these in here, and let's just mark them out as being 1, 0, 1, 2, 3, and 4. The only thing here, well, yeah, this should. The problem here is that this. The problem here is that this is a bad encoding. The reason this is bad encoding is because there's ambiguity in here, right? No, maybe this is actually would work. Let's just take a look. So we see 0, 3, 3, 3, 3. That's interesting. What was 3? Oh, it's just 0. Yeah, okay, that makes sense. Yeah, so that 0 is very greedy in this pattern, right? That's well, we're going to get into this in a couple of videos time when we look at Huffman coding. And this is this goes to show why you can't just compress data like this, right? This is not the smart part of the data compression. What we're actually doing here is just the mechanical part. And the smart part is figuring out how to take your data and then how to turn that into a set of data which is both smaller and non-ambiguous when you come to unpack it. And that's exactly what the Huffman coding is about. It's about taking your data, kind of working out like the frequency of all of the different pieces of data that you have inside, and then generating what's called a prefix code, which is like a non-ambiguous coding, such that when you come to decode, you'll always pull the right thing out. And you need a table of like reference values to get back from the coded value into the actual value. But yeah, that's kind of how that's going to work. So I'm quite happy with this as an API, because it both gives us the ability to do something like this, which is, you know, kind of useful in itself. Probably how we would use it in the let's just take the 0 thing away so we don't match any ambiguous zeros. Like for const pattern of iterator, we could do something like this, and then that's going to allow us to get at each individual one, and we can run like a block of code in here, right? So can actually do something with the values that we get out. So I think this is going to be a nice API. This is going to work for what we need it. I'm going to take this this bitpacker code. I'm going to put it on GitHub, which should already be on GitHub by the time you see this. And I'm probably also going to just do a little bit more work to turn it into an actual NPM module, because I think this is a useful piece of code. And as far as I could see, there wasn't just like an individual module that did it. So I think I'll publish this, maybe add some tests, and yeah, it's going to be a nice little tool. I hope you've enjoyed this this little bitpacking excursion. I wanna say thank you for watching these videos. Thanks for watching till the end, and I will see you next.